Thank you, Mattia, and I would like to thank Tamara and Sasha for the invitation. This is joint work with David Dereudre and Adrien Hardy from Lille and Thomas Leblé, which is at Courant Institute in New York. And I'll talk about the sine beta process. As far as I understand, the sine beta process already appeared this week, for example, in the talk of Diane. But I will recall you what is this process, and so linked with one-dimensional log gases. So here, log gases will be on the real line or the unit circle. So it's not going to be discrete models, but continuous models. Okay, so the usual ones. Then I'll introduce our main result, in fact, which is what is called DLR equation for the sine beta. And DLR equation, so it's from Dobrushin, Lanford, and Real. So it's let's say a classical tool from statistical mechanics from the 70s, let's say. So here it's in a context which is a bit different because they were mainly interested in short-range interactions. And I'll talk about what we can do with those DLR equations in hands. And I will mainly focus on showing number rigidity for the sine beta process. And I'll mention another application of CLT for the sine beta. But I will focus in the application part on getting number rigidity. And then I'll indicate some perspectives. So let's start with the log gases. So my gases will be on the real line or the unit circle. So it's n points in the real lines, and they are interacting through a logarithmic interaction. So it's 2D Coulomb gas restricted to the line. So the energy of the configuration, so it's classical. It's the pairwise interaction. So the sum of minus log of xi minus xj, which is nothing but the so it will give the xy minus xj to the beta when I consider the Gibbs measure, and there is a confining potential V, as usual, I would say. Okay, and so the log gas, what we call the log gas, is the corresponding Gibbs measure. So the weight here is exponential minus beta over 2 times the energy of the configuration, and so the logarithmic terms gives you the xi minus xj to the power beta. Okay, so this is, let's say, usual models, for example, related to unitarily invariant models in the framework of random matrices. And in particular, if I take the quadratic potential, of course, we recover the Gaussian beta ensemble, and we know that there are a tri-diagonal model which is due to Dumitru and Edelman. And if we are interested in the C beta ensemble, then you have to consider the interaction on the unit circle without potential. And we know also that there is a pentadiagonal model due to Kilip and Nanchu. Okay, so this is the general framework. And classical potential theory would give us the global behavior, which is given by the equilibrium measure relative to the potential V. Okay, and I won't go into the details of the global behavior, but I will get interested in the microscopic behavior. So it means that I will choose, so on the unit circle, all the points are equivalent, so I can zoom around 0. And in the real models, I have to zoom around a point which is inside the bulk of the limiting measure. Okay, this is classical, and I will assume, for example, that 0 is inside. So I will just multiply all the points by n, and gamma will be replaced by nx1 times nxn. Okay, so I just zoom, and I look at the microscopic model. So what do we know about the microscopic behavior of these log cases? In the case beta equals 2, this has been known for a long time, and we know that the limiting process inside the bulk is the Sine process, and it has so it's a determinantal point process. It has a lot of nice properties that has been studied extensively, and I will focus here on the general beta case. And this is more recent work. So about, I would say 10 years ago, Valko and Virag showed the existence of a limiting point process for the zoomed Gaussian beta ensembles. Okay, so you multiply by n and you look at the microscopic behavior inside the bulk of the Gaussian beta ensembles. This was due to Valko and Virag. And for the C beta ensembles, this was due to Kilip and Stoichou around the same time. I don't remember exactly the date of the papers, but it's about 10 years ago. And so the question is it the same limiting behavior? So the description of those limiting processes are quite involved, so it's not trivial at all to show and to check that the two limiting processes are the same, and this is due to Nakano, and this is what we called the sine beta process. Okay, so this is the process describing the limiting microscopic behavior of a G beta or C beta ensemble. So both proofs are strongly related to the sparse, tri-diagonal or pentadiagonal description of the models. Okay, and from there they could describe the process through a family of stochastic differential equations. So a coupled family of stochastic differential equations driven by a two-dimensional Brownian motion. So I don't know if it has been defined before, but I will just give you or remind you a description. I won't go into the details, but just to see how it looks like. So it looks like that. So you have a family, so indexed by lambda. So lambda is a real or positive real. And so you have a family of stochastic differential equation. So Z here, sorry, here it is. Oh, I don't know how to point. Okay, Z is a two-dimensional Brownian motion. So it's the same for all lambda. And here, so you have a drift, which is given by this function, lambda times a fixed function given by indexed by beta. And okay, so it looks like that. And so it's related. It can be reformulated in terms of the Brownian motion on the hyperbolic plane, and that's why they call it the Brownian carousel. And it turns out that you can show that the solution of this family of equation indeed exists. When you look at the limit, when you look at the limit when t goes to infinity of the solution, then it turns out to be 2 pi times an integer. So for whole lambda, the limit when t goes to infinity is 2 pi times an integer, and it turns out that this integer, so alpha lambda, so the limit over 2 pi, is the number of points of sine beta in the interval 0 lambda, And so if you look simultaneously at the solution for all lambda, you have a description of the law of the sine beta process. Okay? And, so from this description, many properties have been derived. For example, deviations of a number of points from typical behavior, a maximal deviation of the counting, the counting process, etc. So people like Valko, Virag, Holcomb, Paquette worked a lot on this on these properties. So various combinations of these authors. Also, I can mention that very recently, Valko and Virag showed that this sine process can also be seen as the spectrum of a random differential operator, but I won't go into this description. And also, we can mention that this was for G beta and C beta, so for quadratic or zero potential. But it has been, so universality has been shown with respect to the potential V, and this has been done independently by Bourgade, Erde, Xiao, and Lin, and Beckerman, Figali, and Guionnet with different techniques. Okay, so this is what we know about the sine beta, the description of the sine beta. And so the story goes as follows. So about 3 years ago, Silvia Salfati came in Lille to give a colloquium talk, and so she was mentioning in particular work with on large deviations for microscopic behavior of, the empirical measure of the microscopic behavior with Thomas, and she was mentioning that one minimizer of the rate function was this sine beta process. And so David Dereudre, which is more from statistical mechanics, asked me about, but what is this sine beta? And so I say, okay, you look, it's this, you get it from the solution of a family of SDE and stuff like that. And he told me, okay, but it's, I'm working with Gibbs measure, and it should be possible to describe this sine beta as a Gibbs measure, okay? And this is how we started. So we discussed with Silvia, and she told us that Thomas was interested in the question, and we started the project like that. So the initial goal was really to get a more, let's say, physically meaningful description of the sine beta process. So what do we expect? So we start from the finite n Gibbs measure, and as I told you, we rescale, and we look at the empirical measure of n times the configuration. So what would we like to get? So we would like to get, so here I'm just like hand waving, so don't worry, just to give you an heuristic. So as n goes to infinity, we may expect that gamma n should go to something like an infinite configuration. So a radon measure on R or on U. And the energy of the configuration, so Hn of gamma n is the same as Hn of x1, xn. It's just that as the particles are exchangeable, you can express it in terms of the empirical measure. So it should converge to some functional of the configuration. So something like the double integral of minus log x minus y dcx dcy, whatever it means. And so the limiting process may satisfy something like sine beta as a density like exponential minus beta times this functional with respect to the reference process, which is the Poisson process. So of course this is very false. This is very false because we know that only Poisson processes can have a density with respect to a Poisson process. But there are tools, and there is a formalism for like to express more rigorously this kind of heuristics. And this is called DLR equation. So a DLR equation, I showed you right after what I mean with DLR equation. And in fact, it's about describing, so you fix a compact set, and you want to describe the conditional law of the process inside the box, the compact box, knowing the configuration outside. Okay, it's something like that. So let me describe our first result, which is called canonical DLR equation. So you'll see that in fact here here canonical refers to the fact that we have to fix the number of points inside the box. So it goes as follows. So maybe I'll draw a picture. So you have the real line. You fix a box, finite box lambda. Okay, so maybe first, before having the box here, you just you draw a configuration according to sine beta. Okay, so I don't know. So this is an infinite configuration. Okay, on R. Then you fix a box lambda, which is like that. You keep the configuration gamma lambda complement. Okay, so this is the configuration outside the box. You erase the points inside, but you keep in mind that there were 2 points inside. So you keep track of the number of points inside the box, and you will redraw the 2 points according to a measure, which is a Gibbs measure, which is given by exponential minus beta h of eta plus some function m of eta gamma lambda complement, which is so h eta is the interaction of the configuration inside with itself. So eta h of eta will be just double integral of minus log of x minus y d eta x d eta y, okay, which is nothing but a double sum, and x has to be different from y. And m, so we call it the move function, expresses the interaction between eta and the exterior configuration. Okay, and then you'll get two new points, and this is your. So what it says is that the new configuration has the same law as the initial one. Okay, and so B here is what we call the Bernoulli process. It's just you draw 2 points uniformly in lambda, and then you define the measure with these guys. Okay, so so maybe I will, as it is a little bit tricky to understand, I will give you a more formal statement, a more formal writing of the equation. Sorry, I just wanted, before going further, I just wanted to mention that such a description has been already obtained by Sasha Buffetov for the Sine process. Okay, relying on the determinantal structure of the Sine process, and this structure has been used by Arnaud and Nina Diaz. But I'll go back to Arnaud's Mignadia's work a bit later. So let me give maybe a more proper statement. So it's exactly what I say. You draw. Sorry, this is not working. No, this one. Oh, sorry. Oops. So I draw a configuration according to sine beta. So this was the initial one. Then I keep the configuration outside, and I redraw the same number of points according to a certain density, which is, so here you have the interaction, this is the H, and something depending on the exterior configuration, which are the move functions. Okay, is it clear? What is the meaning of the DLR equation? So I'll try to explain you what are the technical difficulties, the technical issues. So how would you like to define those move functions? Okay, so it's the logarithmic interaction between the configuration inside and the configuration outside. Okay, so in fact, what you have to do to define such a quantity is just to define the quantities inside a very big box containing your lambda. Okay, so here you have a minus r, let's say, and you define the interaction between the configuration outside and the configuration outside lambda, but inside minus r, and you want to let r go to infinity. So can you do that? Well, let me rewrite this quantity as, so it's a certain function of eta. I mean, it's a certain function of y integrated over the outside configuration. And so it's not to say that it's x, if x is inside lambda, this behaves like log of y, so it's going to be hard to make it converge. So in fact, a better option to define the move function is just to look to introduce a reference configuration, eta 0, which has the same number of points as eta inside lambda, so this is why it's called move function, because in fact it's not the cost of having the correction eta, but it's the cost of moving the points from the reference configuration eta 0 to eta. Okay, so you put your 2 points somewhere and then you move them. And this is much better. And why is it much better? So first this shift, you can absorb it in the partition function. So it depends on lambda and the configuration outside, but there's no problem with that. And then, so this is much better because if x is inside lambda, then this quantity, so this is a measure with mass 0, and in fact this behaves not like log of y, but like 1 over y. And so it's still not convergent, but it's better. And in fact, it's going to be convergent in principal value. And the idea is the following. The idea is that you know that your sine beta, you have normalized things so that the average density of points is 1. So in average, it behaves like just the Lebesgue measure. And this is convergent, okay? Not in absolute value, but if you take here a symmetric interval, this is going to be convergent. And what you have to do is to compare your configuration, so a typical configuration under sine beta, with the Lebesgue measure. So it has to be well spread in a sense. And the tool for that is called the discrepancy, okay? So the discrepancy is just the difference of the discrepancy of a configuration gamma inside an interval is just the difference between the number of points of gamma inside your interval and the Lebesgue measure of the interval. And so, so in average, so the expectation of a discrepancy is just 0 as the process has average density 1. But what you want to control is the variance of the discrepancy. Okay, this will help you to make the move function. This will be the crucial point. And so this is pretty hard to get, but fortunately it has been made before. It has been done by Thomas and Silvia Safati, made it in their paper on large deviations. And they got that the expectation under sine beta of a discrepancy, so the variance of a discrepancy is not much than R, so behaves like the volume, and this is enough to get a good control on the the convergence, and to show that the move functions, once you put the reference measure, is well defined. Okay, so for those that are familiar with this kind of thing, it's a bit like the Gaussian ID. It means that you cannot consider your configuration of points. So those are charged particles. Okay, so they have to be balanced with something. Okay, and so you have to compare them, or to consider that there is a uniform charge somewhere compensating the total charge of the configuration. Otherwise, it cannot be a stable physical system. Okay, this is this kind of thing. Okay, so here at least we know that our equations make sense. It's well defined, but now we have to show that the sine beta indeed satisfies the equations. So we start with a reference model. So we start from C beta, because we know that C beta converges to the sine beta at the microscopic level. So we show, C beta, in fact, so it's a log gas on the unit circle, and if you want to write it on the line, in fact it's a log gas with a pairwise interaction at a log of sine of x minus y. Okay, so it's almost the logarithmic interaction, but you have to, of course, take into account the periodicity. So it's really algebraic computation to show that at the DLR equation at the finite level for this model, and then you use the convergence to the sine beta, so combining Kilip and Stoichioù convergence and Nakano, showing that it's the same process as Valko and Virag one. Okay, and so of course here there is a lot of approximating steps. So you have to control the convergence of C beta to sine beta, and also to various approximating steps, but it's the main starting point. Okay, and then we obtain canonical DLR equation. So again, canonical means that both the outside configuration and the number of points in lambda are fixed. So at this point, okay, we are happy because we have a description of the sine beta as a Gibbs measure, which is in a sense satisfying. But okay, is it useful? And so yes, it's useful, and we have now two different applications. And the first application, the application we work with in our work with David, Adrien, and Thomas, is the notion of number rigidity. So what is number rigidity? Well, you consider a point process. So a point process is a probability measure on random measures of configuration of points, and we say that it's number rigid if for any compact set lambda there exists a measurable function f lambda such that p almost surely the number of points inside lambda is a function of the number of points of the configuration outside. Okay, it means that if I for rigid number rigid point process, if I give you the configuration outside lambda, it fixes the number of points. Okay, so I cannot have configuration with 2 points and configuration with 3 points with finite probability. Okay. Of course, I mean not of course, but like f lambda is not explicit at all, and I mean it's not constructive. It's just the existence of the point process. So it's a pretty fascinating property of point processes. And for example, it's exactly the contrary of Poisson processes, because for Poisson processes, the number of points inside is completely independent of the outside. So it's really the opposite. Okay? Here it's really deterministic. So we have a few examples of point processes that are known to be rigid. A lot of them are determinantal point processes. It's in a sense linked to a repulsion phenomenon, like if points are repelling each other a lot, in a sense, it determines the number of points. I mean, you don't have room to add points to your configuration, but it's a bit tricky. I mean, you can have strongly repulsive interaction, but the process is not rigid. I mean, it's really, it's also linked with hyperuniformity, but the links are pretty subtle. In particular, so Sasha showed that the sine process, so for beta equals 2 is rigid, and Reda Shaibi and Joseph Nash-Noodle also have shown that the sine beta is rigid. And all proofs of rigidity of number rigidity that we know rely on a strategy, on a result of Subro-Ghosh and Yuval Perez, saying that, so it boils down to a fine control on the variance of linear statistics of the process. So what you have to do to show rigidity is, so you fix your lambda, you fix an epsilon, and you construct a family of compactly supported functions that are one on the lambda you are interested in, and you have to control the variance of the linear statistics here. So here you see that for the x that are on gamma lambda, the contribution would be exactly the number of points inside lambda, and so you have to show that you have a good control on this. So if you have such a control on the variance, P is rigid. So of course, for determinantal point processes, we have nice tools to compute 2-point correlations or variance. Okay, but for sine beta, for sine beta, there were, so Shaibi and Nash-Noodle, they have a very nice and short paper showing the rigidity, but it's relying on previous papers with complicated, let's say, representation, theoretical computation of moments of the sine beta. Okay, so here we have, I think, completely different approach of number rigidity, relying on DLR equation and on various tools of, let's say, classical statistical mechanics that I'll try to introduce. So I'll give you a flavor of a proof, although it's a bit like technical, but okay. So let's go. So in fact, we don't show directly that the sine beta is number rigid, but we show that any process satisfying our canonical DLR equation is number rigid. Okay. So I rewrote the DLR equations, but here it's not necessarily sine beta. Maybe there is another solution, and it would be also number rigid. And of course, as we know that sine beta is a solution, we got that sine beta is number rigid. So how do we show this, this theorem? And sorry, so before going into the proof, usually when you look at the notion of rigidity, another notion going together is tolerance. It means that, so you say, okay, once I have a configuration outside, I know the number of points inside. But are there other quantities that are determined, or is it the number of points is the only one? It means that given the number of points, you have your process will have a positive density with respect to the Lebesgue measure on lambda. And if the number of points is the only quantity to be fixed, then the process is said to be tolerant. And here the tolerance is for free because the density is written here. You got the density directly. So we got, if we show that it's number rigid, we also got for free that it's tolerant, okay? In the Gauche-Perez strategy, usually it's a bit more difficult to show tolerance, okay? And there are examples where, for example, you have number rigidity and you have also rigidity for the barycenter of the points. So there are the determinantal point processes for which the barycenter is also fixed. But here we get for free that it's tolerant. Okay, so let's go a bit inside the proof of number rigidity. Sorry. So before getting into the proof, another remark. In fact, so I told you that what was written before, so this thing, so when you condition on the configuration outside and the number of points inside, was called canonical DLR equation. But in fact, if this is a deterministic deterministic function of gamma lambda complement, I can get rid of the conditioning by the number of points, and this is what is really called DLR equation. Okay, so number rigidity gives you that in fact your canonical DLR equation or full DLR equation. You can get rid of the conditioning. Okay, so how do we go there? So we use a concept which is also classical in statistical mechanics, which is called the Campbell measure. So the Campbell measure is the joint distribution. So it's you take a typical point in the configuration gamma, and you look at the joint distribution of the point and the neighborhoods, that's the configuration minus this point when you okay? So if I write it more formally, so you take f, which is a function of a point and a configuration, and the expectation under the Campbell measure of this function is just the expectation of, so here you make an average of the function over all the points, so this is typical point, and then you take the expectation over the configuration. Okay, and this is called the Campbell measure. And you can extend here the definition to CPN. That would be a typical n tuples of points in the configuration gamma. And so what we show is that if you have a point process P satisfying canonical DLR equation, then this Campbell measure can be written, so it has a density with respect to the Lebesgue measure on R times a certain measure on the configuration, and the density is given like by exponential minus beta times. So this is in fact the cost of moving one point from 0 to x in your configuration. Okay, so it's exponential minus beta times the cost of moving a point from 0 to x in the configuration gamma. Okay, so this can be done. And the same holds for n. I wrote all the equation for n equals 1 because otherwise it's a mess. And then we go by contradiction. We show that for a configuration which is not number rigid, well, if it's not number rigid, it means that when you have a typical configuration, then with a finite energy at a finite cost, you can remove a number of points, maybe not one, but a bunch of points, or add a bunch of points. Okay, and this is translated mathematically by the fact that you measure Q, so Qn in the case of Cpn, is absolutely continuous with respect to P, because it means that if we remove n points for gamma, the distribution that we obtain looks like P, but with different weights. Okay, so I can remove n points is translated in the fact that the measure Q that I wrote here has a density with respect to the initial measure P. Okay, so we assume that n equals 1 here, and so Cpn has a density with respect to Lebesgue times P, and here the cost, so this was already there, and then I have another density, which is a certain function psi of gamma, and this is in a sense the cost of creating one point in a sense. And in statistical mechanics, this kind of equation of the Campbell measure expressed in terms of the initial law are called G and Z equation, for those that are familiar with this kind of concepts. And in fact, there are some compatibility relations. So you can say, okay, if I had 2 points, if I had first x and then y in the configuration when x is already there, it should be the same that if I do it in the reverse order. And this gives you some compatibility relations between the psi's. Okay? So here you have, in fact, more or less the cost of moving 1 point from x from y is logarithmic. Okay, so now with all this in mind, we can go inside the proof itself. So I'm running a bit out of time, but okay, let's go. So I will look at so x and y will be 2 points, and I will look at the joint law with the configuration. I mean, in the neighborhood, in that neighborhood. So I look at CP2 of x being in 1, 0, 1, and y being in k plus 1, and k will go to infinity. So this is something like the correlation functions between the number of points in 0, 1 and the number of points in k plus 1. And in fact, I cheated a little bit in the paper. We cannot handle directly the 2-point correlation, but we have to get some truncated. So we assume, we truncate by the number of points in those intervals being bounded by some constant. So once you truncated, you have a uniform bound which does not depend on k. Okay, so this is false as it is, but okay, you can truncate, and then you'll play with what you know about CP2. So you know that CP2 has a density with respect to the Lebesgue measure on x and y and the law of P. So you can rewrite it like that. So I'm going a bit quick, and then what you are doing is, in fact, you will change variable, and you will move your, the process that you are looking at are stationary. So you will, in fact, shift the interval k plus 1 into 0, 1 or 1, 2, And so here, gamma minus k is the shifted configuration. And okay, so this will be at some cost. So moving a point from, typically from k to 0 will cost you k to the power beta, okay, times something. And so what we can show is that by the ergodic theorem, well, in fact, this quantity, so the Cesaro mean of this quantity without the k beta will be bounded. So 1 over n sum over k of this guy will be bounded. But when you add the k to the power beta, it will converge to infinity. This leads to a contradiction. Okay, so it's really the fact that we have a long-range interaction going to infinity that gives you the contradiction. Okay, oops. So let me now conclude. And I would like to mention that so Thomas could use also the DLR equation to get a CLT for sine beta. So you'll see that the CLT looks, I mean, so you get variance that again involve the h1/2 norm of your test function. So it looks like Johansson and like the variances that that Alisa showed us in the previous talk. Just so in many contexts for showing CLT, as Alisa explained us, the starting point is loop equation, okay? And here, but here for sine beta, I mean, at the finite L level, you have loop equations. But for the sine beta, for the limiting process, you don't have loop equation. And DLR equation play the role, in fact, of the loop equation. And then Thomas, so he started from there. And then he could use optimal transportation arguments to compare the initial measure, limiting measure, with the measure with a drifted potential, drifted by phi, which is the usual strategy. So that was useful also for this. So this is not really a perspective. I mean, it's another application. And then, so the question we can ask is, can we show number rigidity for other Gibbs point process, so airy beta, for example, or things like that? And in particular, we are working also with the same team on two-dimensional Coulomb gases, but it's hard. It's hard because it's much harder to show that the move function exists. So even to state the DLR equation is complicated, and also we don't have a nice starting point as the C beta E. I mean, there's no really a model for two-dimensional beta case. So it's tough, but okay, we'll see. And also, you can ask about the unicity of the solution of DLR. I mean, sine beta satisfies DLR, but is it for only one? And the answer was, the question was answered positively in the paper of Keulos and Miniadias that I already mentioned for the sine beta. So in fact, they look at, here lambda is minus RR. They look at the conditional measure and they make R goes to infinity and they recover the sine process inside the box. So it's a way of showing unicity of the solution. But here, I mean, it's, so they rely on the determinantal structure and, okay, again, doing some Riemann about tuning, but here, okay, we can raise the question. We don't have a clue about unicity of, I mean, we think it's unique in dimension 1, but we don't have a proof. And thanks for your attention, and the picture is to... It's a homemade two-dimensional log gas.
Thank you very much. Are there any questions?
So can you do something similar, the randometric soft edge, so for airy beta instead of sine beta?
I was asked the very same question this morning at the breakfast, but no, I don't have an answer. But it's as I was raising the question of rigidity for other Gibbs measures, so yeah, it's airy beta would be a natural candidate to investigate, but I don't know.
Do you think you could handle when beta goes to 0? I mean, or at least something becomes very small, and then the repulsion will, of course.
Also, I should have mentioned that there were, so in the slides of previous results, so the asymptotics when beta goes to 0 was investigated by Allais and Dumas. So could we look back at those kind of questions in the framework of the DLR equation? I don't know, but yeah, maybe it would be a
because I mean, I think what they do is only the global regime. I mean, they don't have local information, and the sine betas, of course, where you have local information. So
yeah,
it would be very interesting.
Yeah, I don't know. So it's a very interesting question. Thanks.
More questions?
I don't know if anyone's like, who drew that picture?
Actually, with Adrien, we were writing like a review paper. I mean, like a broad audience paper on determinantal point processes. And each time I heard, okay, this is repulsive point processes or natural in the brain. I mean, when you ask people to draw a point process, they won't draw something like a Poisson point process. I mean, they don't want to have like clusters and gaps and things like that. And everybody said, okay, like a 5-year-old would draw something much more looking like Ginibre than like. So it was 1.5 years ago, and I had like 3 5-year-olds in my living room, so my daughter and 2 friends, and this is one of the pictures. So I tried, like just put points, and so this is the best one. So it's out of a sample of 3 5-year-old kids.
Thank you. Okay, so that's the end of the morning session. Let's thank all the speakers again.